Students, in this lesson we are looking at linearity and continuity of graphs. Let us begin with the first graph here where I have different points. Something like this we call discrete data. So this graph, the first graph here, is what we call discrete data. And discrete data is basically points not connected on the graph. So points not connected. And when we look at the domain, we are looking at all the individual x values. So in this case, we have 2, 3, 4, 2, 3, 4. We have -1, -2, -3, -1, -2, and -3. So these are the domain values. When we consider the range values, remember range values are the y values. So I would have 1, 4, -1. So 1, -1, 4. We have 0. We have 2 and -3. 2 and -3. So once again, discrete data is data on a graph when the points are not connected. When the points are connected, we call that a continuous data. And that means that all the points are connected to each other. And when I'm looking for the domain for something like this, the domain really, if you think about it, this graph goes all the way to the left and all the way to the right. So we can say that it's going to be all real numbers for x, for the domain. If we consider the range, this graph also goes all the way up here and all the way down. So we can say all real numbers. When the graph is neither discrete nor continuous, we say the data is just neither. It's not discrete and it's not continuous. Okay, so these are some examples of discrete, continuous, and neither data on a graph. The next thing we're going to do is we're going to look at data that may be linear or non-linear. So let's get to that here. I need to erase this. Here we go. So, and actually one example really quick where we can decide whether the data is discrete, neither, or continuous. If I look at this example here, well, it's not discrete because the points are connected. And so we would say this is continuous. All the points are connected. There are no breaks in the graph. So this right here would be called continuous. Continuous data. And in real life examples, the difference between discrete and continuous, discrete is when you have data that cannot be broken up. So an example could be when you buy a cup of coffee, you have to buy whole cups. So that would be discrete data. If you can buy parts of something, like if you go to the gas station, you can buy half a gallon, you can buy a quarter of a gallon, that would be continuous data. So in real life examples, that's the difference. Now the next thing I need to go over is whether data is linear or non-linear. So an example of a linear function, the word linear means it's going to be a line. So if I consider this graph here, this graph here is a linear model. It's an equation that it's a linear equation. Why? Because it's a line. And we know it's linear because on the x-axis, it's increasing at the same rate each time. So notice it's going by 1, 1, 1, 1, 1. And on the y-axis, it's increasing by 15, 15, 15, 15. So when the change is the same for the x and the change is the same for the y values, we can say this is a linear model. And sometimes we can look at a table and decide whether something is linear or non-linear. So for example, if I look at this next table, this next table here, if I consider the x values, let's consider the x values. So the first x, so from 5 to 6, that's increasing by 1. From 6 to 7, increasing by 1. All of these are increasing by 1. So it looks like it may be a linear function. Let's look at the y values. From 35 to 41, it's increasing by 6. From 41 to 47, also increasing by 6. And 47 to 53, increasing by 6 as well. And the last one, 53 to 59, increasing by 6. Notice how this change here, it's constant. It's changing at the same rate, as well as the x values. It's constant, so we can say that this is also a linear model. One example where I'll show you where we have data that does not represent a linear model would be something like, give me 1 second. Let me just erase this, clear this. If I look at this data here, let's consider the changes on the x-axis, and let's see how it's changing. From 1 to 2, it's increasing by 1. 2 to 3, well, all of these seem to be increasing by 1. So it looks like it's a linear model. Well, let's go on the y-axis. 3 to 5, increasing by 2. 5 to 11, it's increasing by 6. 11 to 21, increasing by 10. 21 to 35, increasing by 14. Well, on one side is constant, but on this side, it's not constant. So we can say that this is a non-linear model or non-linear data. That means when you graph this, it's not going to form a line. When we have an equation, we can also determine whether that equation is linear or non-linear. For example, if I consider this equation here, let me do that one more time. If I consider this equation, y is equal to 2x plus 5. Notice the exponent next to the x. Well, there's no exponent here, which means that that exponent is a 1. So that exponent is a 1. If we don't have an exponent there, it's because it's a 1. And if that exponent is a 1, this exponent here is a 1, we can say this is a linear equation. That means if I was to graph this, if I was to make a table, just really quick, let's make a table here. Let me show you why this is a linear model. I'm just going to choose values for x. I'll choose 0, 1, 2. Notice they're increasing by 1. If I take 0, substitute it for x, 2 times 0 is 0, plus 5 is 5. If I take 1, substitute it into x, 2 times 1 is 2, plus 5 is 7. If I take 2, this 2 right here, substitute into x, 2 times 2 is 4, plus 5 is 9. Notice the change here is by 2, it's increasing by 2, increasing by 2. On this side, it's increasing by 1, it's increasing by 1. So we know this is a linear function, a linear equation. There are times when the data or the equation is not linear. Let me find one example that shows when this is not linear. If I consider this equation, let me expand this, make this bigger. All right. Okay, so here I have y equals 3x squared minus x plus 5. Again, let's look at the this exponent right there. You see that? It's not a 1. So this is not linear. This is non-linear. In fact, this is something called a quadratic function, and we'll look at this later on. Quadratic function. So when you graph something like this, we don't get a line, we get something else, we get a curve, and we'll look at that later on in the year. So something like this is non-linear. There are equations where they may appear like they're non-linear, but in reality they are linear. So one example could be, and I'll just make one up really quick. If I have, let's see, if I have something like this, y equals 3x squared minus 4x plus 6 minus 3x squared. Okay, so this here appears to be nonlinear. But if we take a closer look, can we simplify anything on this equation? There are two like terms that are additive inverses, which means they cancel each other. And so what we have left is y equals negative 4x plus 6. And this is a linear equation or a linear function. One last thing. A linear function, just let me review this. A linear function must have an exponent of 1. All right. The variable cannot be in the denominator. So the variable x cannot be in the denominator, in the bottom of the fraction. So an example of this could be y equals 2 over x. This is not a function. The x cannot be in the denominator. The x cannot have anything else other than an exponent of 1. So sometimes we'll see an equation that may look like this: y equals the root of x. This is not a linear function. Not a linear function. Sometimes we'll have y equals x to the negative 1. Also, this is not linear. Okay, so once again, to be a linear function, the exponent next to the x must be just a 1. And the variable cannot be in the denominator. No negative exponents either. I hope this makes sense. If you have any questions, please reach out and I will do my best to answer your questions.